P6 waves, end of topic test. This was done before the half term. Make sure that you watch the video and make the corrections in your end of topic test. Question 1. There are different types of electromagnetic waves. Which type of electromagnetic wave has the shortest wavelength? The answer is gamma. Question 1b. A new technology has been developed to charge small electrical devices from the radio waves in the air around us. Explain how radio waves could change a small electrical device. So the first point is going to be the device absorbs radio waves which creates an AC of the same frequency as the radio waves. Next question. The figure below shows the wavefronts of a light wave passing through air into a glass block. Complete the figure to show the wavefronts as they pass out of the air. Now, it's coming from a less dense medium into a more dense medium. So it's actually refracting towards the normal. So if I was to draw the normal like that, right? So it's actually refracting or bending towards the normal. So it should do the opposite when it's actually coming out. So if I draw the normal over here, it should refract, right? Instead of going in that straight path, it should actually refract in that direction. Now, the wave that is refracted should actually be parallel to the wave that is actually coming in. So what we want is to roughly draw a wave, which is that line should actually be parallel to that wave. So these two are roughly parallel to each other, right? And the wave that is actually coming out should have the same wavefronts as this one. So roughly that's about half a centimeter. So if I use my ruler, right, doesn't have to be exact, but approximately it should be about the same wavefronts, right? Note that, right? Wave should be parallel to that entering and that it forms a continuous line, right? And the other important point is that wave fronts of both waves entering and leaving should be similar. It should be similar and that should be parallel. Next question. D. Explain why there is a refraction at the boundary between air and glass. Right? Here you talk about the difference in density and then which relates to the speed. So first point, air is less dense than glass block. Right? 2. So wave front, right, or the wave speed slows down in glass. Right? 3. Since it's entering the glass at an angle, one edge of the wave front enters the glass before the other. This causes it to change direction. Now, I'll show this in the diagram. So let's say that's the glass and the air boundary, right? So remember, relating to this question, right, if that's what I've actually drawn, right, and if that pen is the wave front that you're seeing here, that one of those lines, right? Now if it was to enter straight down perpendicular, right, if the wave is actually moving straight down perpendicular to this, right, both sides of this wavefront, so that's the wavefront, is actually going to get slowed down. So if it did enter the wave like this, then you're going to have a wave which is similar to that. So they will all get backed up, right, because the speed is slowing down. So it's actually going to be like this, right? But it doesn't, the speed changes, but both ends of this wavefront is actually slowing down at the same time. Now, because it's actually entering it at an angle, right, when it enters this part of the wavefront is actually slowing down first, right? When this is slowed down, now this end is still in the air, so it actually moves faster, so it actually changes direction. So the entire thing changes direction like this and then starts moving down. E. The period of a wave in a ripple tank was measured. The period of the wave was 420 ms, which stands for milliseconds, right? Milli means 1000th. So 420 milliseconds to seconds, you'd multiply it by 10 to the power minus 3 seconds. Right? Now, the speed of the wave is 0.6. So remember, speed is given by the symbol v. Calculate the wavelength, which is the lambda, right? The wave period is given by the symbol capital T. So we are using two equations because it's a 5-mark question, right? Wave period equals 1 over the frequency. Now the idea of using this is to calculate the frequency. So frequency would be 1 over t, which is 1 over 0.42, because that changes to 0.42, which would give you 2.38 hertz. Now this actually gives you 2 marks, 1 mark over there and 1 mark over here to find the frequency. Once you find the frequency, you can use this equation V equals F lambda. You're trying to find the wavelength, so rearranging that equation, lambda wavelength is the speed divided by the frequency. The speed is 0.6, which is that, divided by the frequency 2.38. That gives you a wavelength of 0.25. And that's 3 marks for that. Next question. Different parts of the electromagnetic spectrum have different uses, right? So radio waves, right? Microwaves, infrared, visible light, ultraviolet, X-ray and gamma. It's very similar to this first question that was asked here. Which type of electromagnetic have the shortest wavelength, right? So the wavelength is actually, the wavelength is lowest here, wavelength is highest. Right? Use the correct words. The arrow in the diagram is in the direction of increasing. So what's actually increasing? It is the frequency. And decreasing wavelength. Same question was asked before. Drawing around the correct answer. The range of wavelengths for waves in the electromagnetic spectrum is approximately, so that's 10 to the power minus 15 to 10 to the power 4. 10 to the power minus 4 to 10 to the power 4. 10 to the power 4 to 10 to the power 5. Now 10 to the power 15 is smaller than nanometers, right? Gamma waves have much smaller wavelengths, so the answer was the first option, right? Visible light, right, has some of the colors have between the range of 450 to about 600 nanometers, which is 420 times 10 to the power minus 9 meters. So you're looking for a range which is smaller than minus 9, right? And gamma actually has way smaller wavelength than 10 to the power minus 4. The wavelength of a radio wave is 1500, so that's your wavelength. The speed is that. Calculate the frequency. So using this equation, V equals F lambda. Frequency is the speed divided by the wavelength. 3 times 10 to the power 8, which is the speed of light as well. Remember, all electromagnetic waves have the same speed. And divide that by 1500, it gives you an answer of 2 times 10 to the power 5, right? So 2 times 10 to the power 5 is 20,000 hertz. You can write it in standard form, it's fine. State one hazard of exposure to infrared radiation. Infrared radiation is made from any hot objects, so it can cause skin burns, right? So made by hot, not made, rather actually given off by hot objects. State one hazard of exposure to ultraviolet radiation. UV radiation or ultraviolet radiation can cause skin cancer, right, or blindness, right? Constant exposure to UV light can actually cause blindness over time. Next question. X-rays are used in hospitals for computed tomography or CT scans. Give one other medical use for X-rays. There are a couple of other uses for X-rays. I'll write all of them. First one, to detect broken bones. Another one, to detect dental problems, right? 3, to treat cancer. So, state a property of X-ray that makes them suitable for your answer in part 2. So, what property makes it suitable to detect broken bones or to detect dental problems or to treat cancer? So, if I was to link that first point to this, right, it'll actually work for both point 1 and 2 because they are very similar. X-rays are absorbed by bone or teeth, but not by soft tissues, right? And photographic films get exposed to X-rays, right? Now, to understand this, let me show you a really simple diagram. So, when you go for an X-ray, right, you stand in front of a machine, right? Most of us have had an X-ray, right? You stand in front of a machine, and in between the machine and you, they actually place an photographic film, right? Now, you rarely do actually see these photographic films in use now. Now, if let's say you place your hand on top of that photographic film, right? That's my hand, sorry, right? Oh, I've drawn 6 fingers. Oh, maybe, right? There you go. Right. So, if you place your hand and if you pass X-ray through it, what happens is the bones in your hand actually absorb the X-ray. So, when the X-ray falls on the bones or any hard, dense material, it is actually absorbed, and the X-ray which falls on the plain film, the film actually gets exposed. The film is actually darkened when it gets exposed, and what you see is actually the lighter part where the X-ray didn't actually make it. So when they develop the photographic film, you actually just see the bones there. Right. Part 3. The scientific unit of measurement used to measure the dose received from radiation such as X-ray or background radiation is in millisievert. The table shows the X-ray dose resulting from CT scans of various parts of the body. The table also shows the time it would take to get the same dose from background radiation. Abdomen 9 millisieverts, sinus is 0.5, spine is 4. The student suggests that the X-ray dose and the time it would take to get the same dose from background radiation are directly proportional. So, use calculation to test this suggestion. So, if something is directly proportional, if you were to draw a graph, right, of something that is directly proportional, it should be a straight line, which means the gradient at any of these points should actually be equal. So that's the best way to actually prove here. Find the gradient, right, here. So if X-rays, right, are your X value and the time is the Y value, right, to find the gradient, the relationship is X equals Ky, K being the gradient, right? So if you were to draw using these two values, the time, right, which is that, and the dose, right, K would be the gradient. So if I convert 3 years into months, because I want to keep all of them into months, so multiply that by 12, that will give me 36 months, right? So for the abdomen, right, rearranging this equation, K equals X over Y. So for the abdomen, 9 divided by 36 will give me 0.25. For the sinuses, it will be 0.5 divided by 2, which will give me 0.25. And for the spine, it will be 4 divided by 16. Again, that will give me 25. So your answer, he is right. So gradient for all 3 body parts are equal. So yes, it's directly proportional. Next question. A group of students investigate the features of waves. Write the equation which links frequency, wavelength, and speed. So wave speed is the frequency multiplied by the wavelength. The best way to write is the simple equation, or you can write the word equation. That doesn't matter. Now, next, part B. The student wants to determine the wave speed of water waves in the ripple tank. Describe a method the student could use. For 4 marks, this is quite a lengthy answer. So let me explain it, and then I'll write the answer and then show you what the answer is. So in order to find the wave speed, you will need to find the frequency and the wavelength. Now, looking at the setup here of the ripple tank, right? The equipment is the ripple tank, right? Now here you have a motor which is connected to the bar, right? Which is basically a wooden bar which basically moves according to the way the motor spins. So you can actually vary the speed of the motor, and that creates water waves here on this tray. Now, when the water waves are created, the light that is shining from the top will cast a shadow on the card at the bottom, right? So you're actually looking at the shadow of the waves which is on the card. Now, the wavelength, which is the easier part, is actually the distance between 2 of these wavefronts, right? That would be just one wavelength. The easiest way is actually to measure the distance of, say, about 5 or 10 waves, right? So you can actually measure the total distance from there to there by using a ruler. If you place a ruler, right, you can measure the length of, let's say, 5 waves, and then you divide it by 5 and you will get an average, right? That would be the wavelength. In order to find the frequency, if you place a mark on the card, right, and you time how long it takes, or sorry, the other way around, right, you count the number of waves that is actually passing that point, right, let's say in 10 seconds. So frequency is the number of waves per second. So if you divide let's say you count 7 waves, you divide it by 10 seconds, and you will get 0.7 waves per second. So that's how you find the frequency. Once you find the frequency, then you multiply it to get the wave speed. So let me write the answer and show you. So here's an example of a written answer. Adjust bar so it just touches the water surface. Remember, they're asking for the method, so you need to focus on how you would actually do it. Adjust bar so it just touches the water surface. Adjust the motor to produce low frequency waves. So you want to be able to count the number of waves, so it has to be moving slowly across the card. Adjust light so wave pattern is seen clearly on the card. Place ruler at right angles to the waves. Measure total length of 5 or 10 waves. Wavelength equals distance or length that you measure divided by the number of waves, which is going to be the wavelength, right? So for frequency, count number of waves passing a point over 10 seconds. Frequency equals number of waves divided by 10. And finally, wave speed equals f lambda, frequency multiplied by the wavelength. For 4 marks, this is actually quite a lot of information to write, right? So you kind of think, okay, I'm going to get 2 marks for the wavelength and 2 marks for the frequency, and mentioning the frequencies actually involves less writing than the wavelength. But it's something that you should remember because it's a required practical. Next question. Figure 2 and 3 shows the magic coin trick. A coin is glued to the bottom of a bowl and an observer stands where they cannot see the coin. So line of sight. So remember, light travels in a straight line. So if the person is standing there, the light that is actually traveling from here is from this corner of the bowl is actually going just about making it to the eye. Now, the light that is actually reflecting off to the eye, right? So if I was to draw, right? Right, maybe I should have drawn it the other way around, but it's fine, right? So the light that is actually moving in that direction is actually stopped by the wall of the container, so it can't actually reach the eye, right? So another person fills the bowl. The observer and the coin do not move. After the water is added, the observer can see the coin. Explain why the observer can see the coin in figure 3. I've only saw 2 of you actually attempting to draw a diagram for this, right? Always make sure that you actually use the diagram, because although they don't say it, they've given you space for you to do it. So again, if I actually draw a similar line, so the light ray needs to actually touch this edge. So touching this edge, right? If I draw a light ray, right? So light that is coming off from the coin, right? So you're going to get light from the top hitting the coin and then bouncing off the surface of the coin. Remember, the light has to originate from the coin for you to be able to see. So it is getting reflected in that fashion. Right? So answer: light is reflected off the coin travels through the water. 2. As light leaves the water, its speed increases. So going from a more dense medium to a less dense medium, right? So its speed increases. 3. This causes light to refract in the direction of the eye. Again, that's the only point that you actually need to write. If you actually draw this diagram, the first point and the third point is actually evident in the diagram that you're drawing. This is why it's important. Although you might get mixed up over here, you can make your justification using a very simple diagram, right? So part D, some types of waves are longitudinal and some types of waves are transverse. Describe the difference between longitudinal and transverse waves. Again, a lot of you are getting these questions wrong. Always remember longitudinal waves, right? So if the wave or energy direction, if it's going that way, longitudinal waves go back and forth. So the particle is actually moving back and forth parallel to this wave energy direction. In a transverse wave, the particle is actually moving perpendicular to that. So it's moving up and down. So first point, the particles oscillate, or you could say vibrate parallel to the direction of energy transfer in a longitudinal wave to in a transverse wave, the particles oscillate perpendicular to the wave direction. Next question. Now, this question was challenging because you had to actually apply what you actually know about waves and the way it actually moves in different mediums. So it wasn't a straightforward question. Some students did an investigation to study the behavior of waves. The figure shows a ripple tank that can be used to model the behavior of waves. So you have a shallow region and a deep region. Complete the wavefronts on the wave figure above. So show how the wave is refracted as it passes from the shallow region to the deep region. So if it was going in a straight line, so if the depth of both of these regions is actually same, it's literally going to go like that, right? Now, because it's actually coming to a deep region, right, it needs to change direction. So is it going to, so when the pen actually hits, right, so is it actually going to slow down at this end or at this end, right? So is it going to slow down when it goes into the deeper region? Is the wave actually going to slow down? If it actually slows down, then it's actually going to find an obstacle, and this part of the wave, right, this side of the wave is actually, if I label that as A and B, right? So B is going to hit the deep region first. So will this wave front actually slow down first? If that slows down, A is still going to continue on. So the entire wave actually changes direction in that way, right? But if it actually speeded up, if this part of the wavefront speeded up, then it should actually move forward and it should actually turn direction in that direction, right? Now, when you go from shallow region to a deep region, right, wave speeds up. The reason being, in a shallow region, there is more resistance for the water to move actually easily. In a deep region, there's more water, so it's more fluid. In that sense, it can actually move much faster. So how do you draw this diagram? So this is roughly about, right? So you want to draw wave fronts which is roughly the same length over there, right? So about the same length. The question is actually that this point, so when it, because it's speeding up, this wave actually moves further in that direction. And when you are drawing it, this is actually going to be more spaced out. So then this one, because it's actually faster, it actually spreads out, right? So less resistance for the water to move, and then there's more resistance here, right? So explain what happens to the wave as it passes into the deep region, right? The wave speeds up, right? So wave front or fronts move further apart. Some students investigate the properties of waves generated in the figure above. Student A says the waves move water from one end of the tank to the other, while student B says that's wrong, only the waves move, not the water. Suggest what the student could do to decide. So if the water was actually moving from there to there, eventually all the water should be at this end. That's what doesn't happen, right? So what's happening is actually the particle, because remember, water waves are transverse waves. So if you actually look at water waves from the side, you're going to see it like this, right? Now, how would you know or prove that the water is not actually moving in this direction? It's just the wave. So if I float a piece of plastic, polystyrene, or rubber duck, or in real life, if it's a big boat, right, that boat will just simply bob up and down as the water actually wave actually moves in this direction. So how can you find that out? Place a piece of polystyrene or paper on water, right? It would move or bob up and down as the wave passes, proving the water is not moving. Last question. Another student uses a ripple tank where all the water is the same depth. She measures the wavelength to be 0.34 meters. The wave period is 0.42 seconds. Calculate the wave speed, again for 5 marks. Very similar to the question that was given before. Generally in your exam you won't actually get the same question twice, right? So wave period, that is what's given. So you can find the frequency. Frequency equals 1 over the wave period. 1 over 0.42 gives you 2.38 hertz, right? So wave speed equals frequency multiplied by the wavelength. 2.38 multiplied by the wavelength is 0.34, which gives you an answer of 0.8092. Now, the last mark is actually to give your answer in 3 significant figures. Always remember, even if your answer is completely wrong, if you write that and then write your wrong answer in 3 significant figures, you're going to get at least that 1 mark. So 3 significant figures, 0.809, right? And the final mark, 5th mark, is actually for the units. Wave speed is meters per second. So 809. Right, watch the video, pause wherever you need, and then go back and use the video as much as you can to help you out to go through the answers.